everyone and welcome back to my channel A in Economist. So in the previous video, we were talking about how to model a time series process, right? And we have finished covering the classical approach of modeling time series process. In this video, we will be going into the stochastic approach of modeling time series. Now, what is a stochastic approach of modeling time series? Let us understand this. Suppose you have a time series process yt, where this t varies from 1 to n. What does this mean? It basically means that you have this dataset available to you, the value of yt in the first period, that is y1, in the second period y2, in the third period y3, in the nth period yn. So you have this data available to you, the value of a dependent variable y, the variable that we are concerned with, and we know the value of this variable in this n time points, right? In the first time point, in the second time point, and in the nth time point, right? Now, what we say in the stochastic process is that each of these yt's, each of these yt's are random in nature, are random in nature. So let me explain to you what does this mean. So we'll say in the stochastic approach, each of these yt's are random in nature. So we'll say that yt is a function of some random term epsilon t, right? Random means that there is some degree of uncertainty involved in the process of yt. So we will say that yt is some function of random component epsilon t. So in the previous videos, if you have seen my video, I have talked about a time series process consists of two components. First is a systematic component. If you have seen my previous videos, you will know this. First you have some systematic component and secondly you have some random component, right? So mainly time series has these two components. Now in this random component I have defined this term epsilon t. Epsilon t denotes the uncertainty, degree of uncertainty in some stochastic process of say yt, right? So each yt will be a function of this epsilon t. T is from 1 to n, right? Now, since each of this yt is random in nature, what we can do, we can define a probability distribution. We can define a probability distribution on each yt, right? So this is the summary of everything that we will understand in stochastic approach. That you have a time series process, you have to understand this, that you have this data set available with you, and in stochastic approach what we say is that each of this yt that we know is random, in nature. That is why the name is stochastic. Random means you have some degree of probability in everything that you are talking about, right? So each of these yt are random in nature. What does this randomness means? Randomness means that each yt will be a function of epsilon t. I will give you multiple examples on this. We will solve question later on in this chapter. So no worries. If you don't understand this as of now, I'll be explaining it in much detail using questions. So we'll say that each yt can be written using a function of epsilon t's for all t from 1 to n. And since this yt is random in nature, we are able to define probability distribution on each of these yt's, right? Probability distribution on each of these yt's. Now, whenever we talk of probability distribution, you have, I am sure that you have known some of the major probability distribution that we use in statistics. For example, binomial distribution, right? I hope you understand what is binomial distribution, or you might have seen Poisson distribution, or this is the most famous normal distribution, or you might have seen uniform distribution, right? So these are certain major probability distributions that we use in statistics and econometrics. So if you have seen these distributions, if you know the fundamentals of distribution, so you have the idea that what are the features of this distribution. We can find out some of the features of this distribution in terms the parameters that are involving this distribution, right? What are the parameters? Suppose for binomial, the parameters are n and p, right? You have two parameters n and p. In Poisson, you have only one parameter, say lambda, or sometimes you write Poisson m also. So m or lambda, whatever you want to call it. In normal, you have two parameters mu and sigma square, and in uniform, you have also two parameters, suppose a and b. So once you know the parameters, what is the importance of these parameters? These parameters helps you to define some of the features of these stochastic processes. Parameters will help you define some of the features of this probability distributions or probability, or here in terms of stochastic approach, we will be talking in terms of stochastic process. But in terms of probability distribution, what could be the features? We will be talking about the features now. The first feature that any probability distribution or stochastic process is nothing but a probability distribution that I have told you here, right? So whatever features you know of this distribution will also be applied to stochastic approaches. So let's start with these features. The first feature will be the expected value of yt. So yt is your stochastic process that I have defined. So the first feature that we need to know in order to understand the stochastic process better is the expected value of yt. What is this expected value? If yt is continuous in nature, you can define this expectation as this. I'm sure you have seen this formula before, but still I will write u du, right? And when will this be applicable? When yt is continuous. When yt is continuous random variable, right? Or when yt is discrete random variable, you have this u into probability yt equals to u, right? And when will this happen? When yt is discrete in nature. Yt is discrete random variable. So the first property or the first feature of the stochastic process that we need to know in order to understand this process better, in order to model the process better. So we are dealing with the modeling of time series, right? So in order to model something, you need to know the features or the characteristics of that process. So firstly, you need to know the mean of that random variable. This is the unconditional mean, and this is the unconditional mean, unconditional mean or average, right? Simply average or the unconditional mean of the stochastic process, which is defined as this. When yt is continuous, this is the formula. When yt is discrete, this is the formula. And we'll be solving questions on this, so no worries if you don't understand this right now. The second feature that we have to know is the variance. So in this processes also, in this random distributions also, we have defined the mean and the variance and the other features. So what is the mean of binomial? Mean of binomial is np. What is the variance of binomial in PQ? So we define these features in terms of these parameters. That is the importance of parameters I was talking about, right? So in case of Poisson, the mean is simply lambda or simply m. In normal, it is mu, and in uniform, it is a plus b by 2. So you can compare these features of stochastic process with the probability distribution that you already know. This will make your understanding more complete, right? So parameters will help you to define these features that we are discussing one by one. So the first feature we have discussed is the mean. In terms of parameters, you know what is the mean of all these distributions. So if you know the mean, you can, from that, you know the nature of this probability distribution. So these are the features that helps you to model the process better, right? Now what will be the variance of yt? It is simply expectation of yt minus expectation of yt whole square, which is also written as sigma t square, right? So this is the formula of variance of yt. Variance basically measures the dispersion from the mean, right? Variance measures the dispersion of each of these observations from its mean, and this is where way you find the variance. Now, what is the third feature? The third feature is something called the autocovariance. Something called the autocovariance function. Autocovariance function. Now, this autocovariance function is defined as gamma th. Gamma th. Where what is h? H is the lag. I'll be talking about this. So it is defined as yt minus h. So you are why this is autocovariance? Because we are applying the covariance of the same stochastic process yt, but only at two different time points. Here it is t, here it is t minus h. So you are taking the covariance of yt in the period t and some lag value of t, right? In some lag period of t, where lag is defined as minus h. So h can take where h is positive, strictly positive. So h will start from 1. So t minus 1 means you are taking covariance between yt and yt minus 1. 2 means yt and yt minus 2. Since you are taking the covariance of the same stochastic process in two different time points, it is called the autocovariance. Auto means the same. So you are using the same stochastic process, right? Same stochastic process, and you are finding the covariance of that. So this is the autocovariance function, and it is defined as gamma th. So h is basically the lag. If this expression depends on t, you will write t here. If it's not, then you will simply write gamma h, right? And how it is defined? It is basically expectation of yt minus expectation of yt minus h minus expectation of yt minus h, right? So this is the simple formula. You might have seen this in statistics also. And the fourth and the final property that we'll say is the autocorrelation function. Autocorrelation function, or what we say as the ACF function, right? So autocorrelation function or the ACF function. This autocorrelation function comes from autocovariance function only. It is written as this, rho h or rho. Okay, rho th also you can write, but simply we usually write it as rho h, right? What is rho h? It is simply gamma th upon SD. SD is the standard deviation of yt into standard deviation of the lag value that you are talking about. Or more explicitly, covariance of yt minus h root over of variance of, this is variance, right? Okay, let me write it. Variance of yt, variance of yt minus h, where h is strictly greater than 0, right? So this is the autocorrelation function. How do you find autocorrelation? In the numerator, you have the simple covariance that you have found out here, right? In the numerator, you have the autocovariance function, and in the denominator, you have the standard deviation. Standard deviation is nothing but root over of variance. So these two things are same. So standard deviation of yt means root over of variance of yt into standard deviation of yt minus h is root over of variance of yt minus h, right? Where h is strictly greater than 0, it is some lag value. So these are the four features. I hope you understood these four things. So if you have any probability distribution or any stochastic process available to you, you must know these four features. What are the features? Expected value of yt, variance of yt, autocovariance function of yt, and autocorrelation function of yt. And these four features will help you in modeling the stochastic process, which is according to the stochastic approach of time series, right? In the classical approach, I have told you that time series can be broken down into four components: trend component, cyclical component, seasonal component, and random component. And you have also seen how to estimate each of these components, and that will help you in model a time series. But in stochastic approach, there is nothing called these four components, the trend component, seasonal component. These are not present here. Here what we will say, here we will say the individual YT values are itself random. YT values are random. Why they are random? Because they are a function of some random components. Right? YTs are random because they are function of some random component epsilon t. And this epsilon t in questions we will see epsilon t, the distribution of epsilon t will be known to us. Suppose this epsilon t will follow normal distribution, or it will follow Poisson or uniform distribution. So some known distribution with known parameters. These parameters will be given to you in the question. So all you need to do, you have to find the features of this YT in order to model it. Modeling means knowing the distribution in an explicit manner. How will you know the distribution? If you know the mean of the distribution, the variance of the distribution, the autocovariance of the distribution, or the autocorrelation function of the distribution. So this will basically help you in modeling a time series in stochastic approach. Since we are using probability distribution, we are estimating the distribution using probabilities. Since they are random in nature, this process is called the stochastic approach. Stochastic means which is not deterministic, which has some degree of randomness in it, right? So that is about the stochastic approach. I hope you understood the concept, and this is a summary. If you want to take a look at this, you can take a look at this. This is everything that I have mentioned as of now. You have this process. We will assume this random. So we define probability distribution, and we, to characterize this probability distribution, we will use this four properties, right? I hope this thing is entirely clear to you. If you have any questions on this, if you don't understand anything in this approach, you can let me know, right, in the comment section. Okay. Now let us solve some questions on this, right? So let us see the first question. So first question says YT be a time series process defined as this. So if you look carefully, YT is a function of epsilon t most clearly. Here alpha and beta are two parameters, right? Alpha and beta are two parameters of this process. T is nothing but T is 1 to T, right? So these are systematic part. This part alpha plus beta T, this is the systematic part of the time series. Why this is systematic? Alpha is a, a parameter which can take some specific values. There is no randomness. Beta also can take some specific values, no randomness. T also is defined 1 to T. So also there is no randomness. This, the randomness in the picture comes from this part. Randomness comes from epsilon T. So YT is clearly a function of epsilon T. This part is a constant. You can consider it to be some A plus epsilon T, right? A plus epsilon, where A is this part, which is absolutely a constant. You can take this as constant. And the variation comes, or the stochastic nature comes from this random component epsilon T, right? So this will be an example of stochastic time series process. Now the question says where epsilon T is IID normal 0 sigma square. Epsilon T IID normal 0 sigma square. What is IID? IID means independently and identically distributed. Identically distributed. Now I know many students who are confused in this concept, what is independence, what is identical. So let me give you a brief of what this means. So here it says epsilon T follows IID normal 0 sigma square. So 0 is the mean, sigma square is the variance. There is no issue in that. What is IID? Suppose you are considering only two time points T1 and T2. Right? So T can take, for now just assume that T can take only T1 and T2, these two time points. So we have a value of epsilon T1 and epsilon T2. Now, what does identically distributed means? Identically distributed means these epsilon T1 and epsilon T2 both will follow the same distribution, normal 0 sigma square. As simple as that. Identically distributed means they have the same distribution, right? So if you consider two time points, epsilon T1, epsilon, so you will have corresponding random term here, epsilon T1 and epsilon T2. So both will follow the same distribution that the other values are following, right? So this is identical. Now if you have T time points, so you will have this and up to T. right? T1, T2 up till Tt. So this will also follow. You can extend this thing to any number of periods you want, right? Now, what is independence? Independence means the covariance between epsilon T1 and epsilon T2 are 0 for all T1 not equals to T2. This is very important to understand. In if you know econometrics, if you have learned the concepts of econometrics, you will know it is called the no autocorrelation problem. So there is no autocorrelation between the time point T1 and T2. The random terms in the period T1 and in the period T2 are completely independent of each other. Independence means there is no covariance between the error terms in two different periods. So T1 has to be not equals to T2. So these are two different time points, right? T1 and T2 are not equal. If they are equal, then this will be variance, right? Covariance of epsilon t is variance of epsilon t. So that will not do. So we'll say whenever the time points are different, T1 and T2 are different, the covariance or autocorrelation, right? The autocorrelation or the covariance between them is 0. There is no autocorrelation in the error terms, or there is no covariance between these error terms, and hence they are independent. So I hope you understood the concept of identically distributed and independent. So epsilon t's are IID normal 0 t sigma square means that every epsilon t follows the same distribution, that is normal 0 sigma square according to this question, and they are also independent in nature. It means that there is no covariance between any number of epsilon t's you consider. Okay, now let's get back to the question. Let me erase this part. Okay. Now let's focus on this question and let's see what do we need to solve here. So you are given, okay. So let's read the question. So you have this stochastic process where epsilon t follows this distribution. So we need to compute mean, variance and autocovariance, and that will help you in modeling the distribution, right? Modeling means finding out these features basically. So let us do that one by one. Yt is given to you as alpha plus beta t plus epsilon t, where uh, this epsilon t basically follows IID normal 0 sigma square, right? This is given to you and you want to find out the expected value of yt. How do you do that? Expectation of alpha plus beta t plus epsilon t. Simply I have written this yt value here. Now, as I have told you, this is the non-systematic component, this is the random component. And expected value of this systematic component will be as it is. This is from the property of expectation. So you can basically write in this way, right? Now expectation of a constant is a constant. So this will be simply alpha. Expectation of a constant is a constant. So it will be simply beta t. So beta is also constant. T is also, t can take only some specific value. So 1 to t. So this is also constant. So alpha plus beta t will be as it is. What will be expectation of epsilon t? Expectation is 0, right? Normal mu sigma square, mu is 0. So this is simply alpha plus beta t. I hope this is clear. Now you find out variance of yt. What is variance? Alpha plus beta t plus epsilon t. Now variance of a constant is 0 simply. So it will be simply variance of epsilon t, right? So this part we are not considering. Variance of a plus b is, okay, let me write the formula here. What is variance of a plus b? Variance of a plus variance of b plus 2 covariance of ab, right? This is the formula of variance of, so you can consider this to be a and this to be b, right? So here this is a, this is b. Now variance of a is 0, variance of this constant part is 0, variance of b we have written as variance of epsilon t plus 2 covariance of AB. So here 2 covariance of A is what? A is alpha plus beta t and this is only epsilon t. So this part is also 0 from the property that covariance of any constant term and any random term is 0, right? So you have to know the property of covariance, that covariance of any constant term and random term is 0. So there is no correlation between a constant term and a random term. This is very intuitive also. You can understand that covariance of constant term and random term is 0. So there is this part is also 0, this part is also 0. So we'll be left with only variance of B, which is variance of epsilon t here, right? Again, if you have any doubts, you can ask. I'll be replying to that, right? So it is simply variance of epsilon t. What is variance of epsilon t? This is simply given to you as sigma square. So the expected value of this series is alpha plus beta t, and the variance of this series is sigma square. And now we'll have to find out the autocovariance function. The autocovariance function. Let us do that. What is autocovariance? So covariance of epsilon t, this will be covariance of yt minus h, right? This is the autocovariance. So what do you have here? So it is covariance of alpha plus beta t plus epsilon t, alpha plus beta t minus h plus epsilon t minus h, right? You got this, I hope. Yt is this, and yt minus h, simply instead of t you write t minus h, right? So this will give you this. Now how do you find out this autocovariance? Now again, autocovariance will be on the random component, because as I have told you, okay, so let me write this property somewhere. So property, so just remember these two properties, that covariance of constant and constant is 0, and covariance of constant and random term is also 0, right? Covariance between constant, so constant term is, systematic, so you particularly know what is this c, what is this c. So suppose c is 2, so 2 and 2, so 2 and 2 has no correlation or no covariance with each other, right? So this is 0. It doesn't make any sense to find out covariance between 2 and 2, right? So this will be 0. Again, covariance of constant and a random term is also 0. So random term, we do not know what is this term. So we are just trying to model this term. We only know the probability distribution of this term. But constant is, again, we know. So suppose covariance of 2 and some epsilon t. So there is again no correlation, no covariance. So this is also 0. Now in finding out covariance, what you do, you combine each of these term individually. So firstly you will take this alpha and combine it with all this. So okay, just for completeness, I am writing it once. From the next time I will not write this because it doesn't make any sense. Alpha, and then you have alpha here. So firstly you will take alpha and alpha plus covariance of, you will take alpha and then this beta t minus h. So you will find out the pairwise correlation, that will give you your covariance term. Then you have alpha and then epsilon t minus h, plus then you take this beta, covariance of beta t, and here from here you take alpha, plus covariance of beta t minus h, right? I hope you got the process. Alpha with beta t minus h, alpha with this, then take beta t with alpha, beta t with beta t minus h, then alpha t with alpha t minus h, alpha t with alpha t minus h, plus covariance of, start with this alpha t alpha, plus covariance of alpha t beta t minus h, plus covariance of alpha t alpha t minus h, right? So this is the entire expression that we are talking about. Now if you understand these properties, you will see every term will be 0 except the term covariance of epsilon t minus h, right? Every term will be 0 except covariance of epsilon t minus h. Why this is so? Because only covariance of epsilon t minus h will have some positive value if h is greater than 0. I hope this concept is clear. Not h greater than 0, h not equals to 0, right? H not equals to 0. So every other term will vanish and we will be left with, let me remove everything and let me write the expression. Once you are accustomed with this approach, you will be doing it on your own, and you will automatically use the shortcut, or directly you will write it directly. For making you understand, I am writing everything, every little step, but once you are accustomed with this, you will write only this. Just by looking at this expression, you will have this simply. So this is random, this is random, everything else will be 0. There is no autocorrelation, and also they are independently and identically distributed, so we will have something here. Every other term will be 0. Now what will be this? Covariance of epsilon t minus h. What will be this covariance? So we'll write this covariance will be 0 if the value of h is not equals to 0, and this will be sigma square if h is equals to 0. Now again let me explain why this is true. If h equals to 0, what will this be? This will be simply covariance of epsilon t, right? This h is 0, so it is epsilon t. This is simply variance of epsilon t. If you know covariance of the same terms will give you the variance, right? This comes directly from the formula also, so you can check from here. So basically, this lag expression is not there. So this is also epsilon. So these are two same expressions. So expectation of yt minus expectation of yt square will be there, and this will give you your variance. You can do it on your own. So this is simply variance of epsilon t, which is sigma square, right? This is what I have written here. And if it is not equals to 0, so for every positive, every h which is not equals to 0, this terms will be different. T and t minus h will be different. And as I have told you that there is no autocorrelation, epsilon t's are independent. Epsilon t's are independent, which simply means that covariance of epsilon t and epsilon s is 0 for all t not equals to s, right? So I am using this property of independence here. For every t not equals to s, here t and t minus h. So every h not equals to 0 means that t is not equals to t minus h. So for every this two different time points, this covariance is 0. This directly comes from the property of independence, right? So this question is done. I have explained each and every step in very minute detail, given you every explanation. So I hope this will clear your concept. Now I have a second question. So let us solve this question also. So this question is yt is epsilon t theta epsilon t minus 1. So you again have the same distribution for epsilon t, normal 0 sigma square. And so this is pretty simple. Let us solve this. Theta epsilon t minus 1, right? This is what you have. Yes, and epsilon t follows IID normal 0 sigma square. And all you need to do again, do the same thing. Expected value of yt. So expected value of epsilon t plus theta, expected value of epsilon t minus 1. This is 0 plus theta into 0. So this entire thing is 0. What is variance of yt? For that, let me write the formula. Variance of ax plus by. What is this? A squared variance of x plus b squared variance of y plus 2ab covariance of xy. This is the formula. So you have to apply that here. So here you have variance of ax plus by. So a is 1 here and b is theta here. So this will be simply variance of epsilon t plus theta square. So b square variance of yt, b square is theta square variance of epsilon t minus 1 plus 2. Here covariance part will be vanished. still for your understanding I'm writing. So 2 theta covariance of epsilon t minus 1. So again, from the property of no autocorrelation or independence, you know that this thing is 0. So this will be simply variance of epsilon t sigma squared plus theta square. Variance of epsilon t minus 1 is also sigma square, because they are identically distributed, as I have told you that epsilon t, two different time points t and t minus 1, since they are IID, the distribution are identical, so epsilon t will also follow normal 0 sigma square, and epsilon t minus 1 will also follow normal 0 sigma square, right? So distributions are equal, identically distributed. So this is all you have. Okay, no, sorry. So if you take sigma square common, you will have 1 plus theta square, right? So this will be your variance, and this 0 is your expectation. Now then you have to find out the autocovariance. So covariance of yt minus h. So covariance of epsilon t plus theta epsilon t minus 1, and then you have epsilon t minus h plus theta epsilon t minus h minus 1, right? Okay. Now what happens when h equals to 0? When h equals to 0, you simply have covariance of yt, which is variance of yt, as I have told you. Variance of yt you have found out to be this, sigma squared 1 plus theta square. Now consider case h equals to 1. What will that be? Yt minus 1. So this will be covariance of theta epsilon t minus 1 t minus 1 plus theta. So instead of h you are replacing it by 1. So t minus 1 minus 1. So it is t minus 2, right? Minus 1 this. Now just look for the common terms, this and this. So when you do pairwise correlation, only the common terms will be there and other terms will vanish. So it will only come out to be, okay, let me for your simplicity write everything. Epsilon t minus 1. So this term plus covariance of this term and this term. So covariance of epsilon t theta epsilon t minus 2 plus this term and this term. So covariance of theta epsilon t minus 1 epsilon t minus 1 plus this term and this term. So covariance of theta epsilon t minus 1 theta epsilon t minus 2, right? So this is all you have. Next, see that this for independent this term is 0, as I have told you in the earlier question also, that covariance of epsilon t epsilon s is 0 whenever t is not equals to s. So here you have two different time points, t minus 1, so this expression will be 0. Similarly for this expression you have t minus 2, this is 0. For this expression you have t minus 1 t minus 2, this is 0. Only this term will be left. Only this term will be left. So it will, theta will come out, and then you have covariance of epsilon t minus 1 epsilon t minus 1. So theta into this will be variance of epsilon t minus 1. And what will that be? Variance of epsilon t minus 1 is simply sigma square, right? Okay, so for h equals to 1, we found that theta sigma square is the autocovariance. Now what about h equals to 2? Covariance of yt minus 2. So covariance of epsilon t plus epsilon t plus theta epsilon t minus 1, and here you have epsilon t minus 2 plus theta epsilon, instead of t write t minus 2, so you have this. Now if you notice carefully, do we have anything common here? Okay, so this will be pardon, so this will not be here t, so instead of t you are writing t minus 2, so this will be t minus 3, right? So if you notice carefully, there is no term common, right? There is no common term, and if there is no common term, this will simply come out to be 0. Why this is so? Again, the same reasoning, that covariance at two different points, covariance epsilon t epsilon s is 0 whenever t not equals to s. So here no t is equals to s, right? So t is not equals to s, and so every covariance will come out to be 0, so this is 0. So what you can write is that what will be the ultimate expression. Let me remove this. What will be the autocovariance function for this expression? So you can write gamma th equals to covariance of yt minus h is sigma square 1 plus theta square whenever h is equals to 0, and it is simply theta sigma square whenever h is either 1 or it is minus 1. Why minus 1? When we talk about stationarity, we'll talk about stationarity of a time series process in the next video. Then I'll explain why we are taking this counterpart also. So here we have shown that for h equals to 0, this is the expression. This is simply the variance of yt. For h equals to 1, this is theta sigma square. And from the stationarity property, we will also show you that h equals to 1 and h equals to minus 1 will have the same result. Since this is an MA1 process, and for MA1, any MA process is stationary, and for that this counterpart will also be there. I'll be talking about this in the next video. So as of now, just see what I am doing, that for h equals to 1 and minus 1, this will be this, and for any h which is greater than 1, mod h which is greater than 1, mod h greater than 1 means what? If h is greater than 1 or h is less than minus 1. So for any of these values, what will happen? This autocovariance function will take the value 0. Why this is the case? Because as I have told you that for h equals to 2, this value is 0, and as you go on doing this, h equals to 3, h equals to 4, so on and so forth, you will see there is no common term here. And if there is no common term in this covariance argument, then every covariance will come out to be 0, and that is the case for this MA1 process. So for MA1 process, I have not defined MA1 process, but this process is MA1. I'll be going into this everything in details in later on video. So h equals to 0 will give you the variance. Variance is the same as autocovariance here. For h equals to 1 or minus 1, this is theta sigma square. And for every other h, that is h either can be mod h greater than 1, so h is greater than 1, or h is less than minus 1. So since these counterparts will have the same value, so for every other h, every other lag value, this value will be 0, and this will be your answer. So for this question, we have found out what is mean, what is variance, and what is the autocovariance, right? Okay. Now this question is the same question, similar question, theta epsilon t. So we have done, what we have done is epsilon t plus theta epsilon t minus 1. Now for your homework, I have given you a simpler question. So please do this homework. It's pretty simple. You know the distribution of epsilon t. All you need to do is the expectation, the variance, and the autocovariance. You can, verbally also do it. You don't need to write everything. So you can do it on your own, just for your own clarity and to understand the topic better. So please do this question. And finally, I have a fourth question. Now I have given this question because this question is a little different from what we have seen up till now. So let's see, yt is phi yt minus 1 plus epsilon t. So as of now, the questions we did, yt was only a function of epsilon t. Here also yt is a function of epsilon t, only epsilon t. And in the first question also, what we did, it was a function of t and epsilon t, only epsilon t you can consider. So everything that we have done so far, yt was only dependent on epsilon t. But here what you see is that there is a recurrence relation here. Yt is also dependent on its own lag value. Yt is dependent on its own lag value and also on yt. So epsilon t. So yt is now a function of yt minus 1 and epsilon t instead of only epsilon t, right? And later on we'll explain that this is an AR1 process and how to deal with that. But as of now, if you are given this question, how do we handle this kind of question? So here you have to find out the same things, expectation, variance and autocovariance. But here you have a problem, a little problem. What is the problem? Here yt minus 1 is also a random term, right? Yt minus 1 will have its own distribution. Yt minus 1 will be pi yt minus 2 plus epsilon t minus 1. So this will be the distribution. So every term, in every yt term you have this recurrence relation. So if you find out yt minus 2, you will have this kind of recurrence relation and so on and so forth. So since every yt term is also having a recurrence relation and the distribution of yt is not known to you, you have to find out the distribution of yt. So you cannot simply take the expectation on this thing. So if I write expectation of yt is expectation of phi yt minus 1 plus epsilon t, you will not be able to solve it without further information because you will be stuck here. So let me write yt minus 1 plus expectation of y epsilon t, right? So you know this thing, this is 0, this is given to you, but what will be this? This we don't know, right? Because we don't know the distribution of yt minus 1. Yt is a random term, yt minus 1 is also a random term, but only the distribution of epsilon t is given to us. The distribution of yt minus 1 is not given to us. If yt minus 1 also is been specifically mentioned follow some particular distribution, then this value is known. But here, as the question is framed to us, this yt minus 1 distribution is not known to us, and for that we have to take a separate approach. We have to take a separate approach in solving this question. So let me show you how we can do this. Okay. So here we will use something called the lag operator. We will use something called the lag operator, which is denoted as capital L. And what is our aim? Our aim will be to convert yt to a function of only epsilon t. Right now, what is given to you is that yt is function of this and this, but the aim of your converting will be so that yt is a function of only epsilon t, right? You can write yt in the using a series of epsilon t. Now how will you do that? You will use lag operator. How to use lag? Lag of, so lag comes in before the expression, or before the stochastic process, right? So if you write lag of yt, it simply means yt minus 1. So here lag power is 1. Now if you write lag square yt, it will mean yt minus 2. If you write lag cube yt, it means yt minus 3, so on and so forth, right? So what you see here is that the degree of lag is the comes here. So lag means that basically the period you are considering the lag terms in this way. Nothing but writing. You can write this to be lag of yt, right? So this is something very useful in solving this kind of question. So you use the lag operator. Lag simply means if you take the lag according to the degree, this thing will change. So lag to the power 1, the degree is 1 of yt means simply yt minus 1. Lag 2 yt means yt minus 2, so on and so forth, right? Now if you use this kind of thing, how will you write this given expression? How will you write the given expression? So here yt is given to you as phi yt minus 1 plus epsilon t. So simply phi lyt plus epsilon, right? Now take this on the left hand side, phi lyt epsilon t. Now what you can do, you can take this yt, okay, write in this way. take this yt common. So what you have, 1 minus pi l, right? Take yt common, so you will 1 minus pi l equals to epsilon, right? Now from the using invertibility property of yt, we have, from the invertibility property of yt we have, so let me write in this side, yt can be written as 1 minus pi l inverse into epsilon. So please understand this thing, it's very important for you to understand. So what I have done, I have written yt minus 1 using this lag operator, then I have taken this expression on the left hand side and simply take yt common, and you have this expression. Now you want to write yt only in terms of epsilon t, right? Your aim is to, as I have mentioned here, yt is, we only want to express yt in terms of epsilon t. Why? Because we know the property of epsilon t, we know the distribution of epsilon t. Unless we know the distribution of the argument, we cannot find or we cannot model yt, right? That is why what we have done, we have changed yt in terms of epsilon t, and using the invertibility property, invertibility means this can come out here in the form of inverse, right? Okay, I hope this, up till this is clear. Now you know something. What is 1 minus x inverse? 1 minus x inverse can be written in this form, 1 plus x squared plus x cube plus so on. So this inverse thing, if you compare, this inverse thing can be written as an infinite series, which looks like this, in this form, 1 plus x squared plus x cube and so on. So if you do the same thing for this, what will you get? Yt can be written as 1 plus phi l plus phi squared l squared plus phi cube l cube plus so on into epsilon, right? So I have simply written this inverse in this form. Okay. Next, do the multiplication. So firstly you have epsilon t, then phi is as it is, then L of epsilon t, right? So you are just multiplying individually the terms. So epsilon t is as it is plus phi of L epsilon t is epsilon t minus 1 plus phi square L square epsilon t is epsilon t minus 2, phi cube, this is phi cube, L cube epsilon t is epsilon t minus 3, so on and so forth. And if you look at this expression, this is our desired expression. This is our desired expression. Why this is so? Because here yt is a function of only epsilon t and lag values of epsilon t, right? So if you see, yt can be expressed as epsilon t plus phi is a constant or a scalar term, epsilon t minus 1, epsilon t minus 2, epsilon t minus 3. So what we have done here is that we have converted yt in terms of epsilon t. Now the epsilon t and the lag values of epsilon t, since we know the distribution of epsilon t and its lag values, that is from the IID property that I have mentioned. Now we are able to find out, after this transformation, we are able to find out the mean of yt, variance of yt and autocovariance of yt. So let's quickly do that, and with that we will end our session. So what will be expectation of yt? Expectation of this epsilon t plus theta epsilon t minus 1 plus, not theta, this is phi, right? Epsilon t minus 2, yeah, plus phi cube epsilon t minus 3 plus so. What is expectation of epsilon t? Okay, let me write this. So this thing is 0 because okay, from this property, right? It follows normal 0, 1. So expectation value is 0 plus phi into 0 plus phi square into 0. So everything is 0 and the expected value of epsilon yt is 0, right? Now find out variance of yt. Variance of epsilon t plus phi epsilon t minus 1 plus phi square epsilon t minus 2 plus so on. So variance of epsilon t plus phi square. So this coefficient will be squared. Then variance of epsilon t minus 1 plus phi to the power 4. This will again be squared. Variance of epsilon t minus 2 plus so on. The covariance terms will be 0 again from the IID property, right? What is variance of epsilon t? Sigma square plus phi square sigma square plus phi to the power 4 sigma square plus so on. So if you take sigma square common, you will have 1 plus phi square plus phi to the power 4 so on. Sigma square upon 1 minus phi square, right? This is from the property of series, you know, GP series formula. Sum of infinite terms is 1 upon 1 minus phi square when this phi square is less than 1. So this can't be 0, right? 1 minus 1 cannot happen. So this phi square should lie between this. So what is variance? Variance of yt is simply this, whenever phi square is less than 1, right? Now, so we have found what is expectation and what is variance. Now the third thing is autocovariance. So gamma th. So this can be written as this and this, right? Now firstly find out covariance of yt minus 1. We'll start from 1 because we know for 0 it is only the variance, right? So now what do you do? Write yt from the first expression. From the first expression, what is yt? This is just to simplify our calculation, nothing else. This, and then you have yt minus 1, right? So this I have written as it is and this I have written from here. Now take pairwise correlation, right? So covariance of this phi will come out yt minus 1 plus covariance of epsilon t yt minus 1. Now what is this? What is this? Covariance of yt minus 1 is variance of yt minus 1, right? Plus this part. Now this thing is important. Covariance of epsilon t yt minus 1. As a rule of thumb, you must remember that covariance of epsilon t yt minus j is always 0 for j is greater than 0. I know this thing can be complicated to you, but you will see this expression multiple times. We will solve when we go into some special stochastic processes and we'll discuss their properties. You will see that this thing will come multiple times, so it's better that you know this expression and know how to handle this. So covariance of epsilon t, so the error term in the tth period has a 0 correlation with all the yt values before tth period. So j is positive means this value should be less than t, right? T minus 1, t minus 2, t minus 3. So epsilon t has 0 correlation. You can understand this intuitively also, that epsilon t is the error that is coming from the process in the tth period, right? Epsilon t is related to yt, but for the previous periods it doesn't have any correlation. So graphically, if you understand, so here you have epsilon t, right? This epsilon t arises from the distribution of yt, or yt has a correlation with this, right? Epsilon t is correlated with the distribution of yt, but for the previous terms yt minus 1, yt minus 2, yt minus 3 and so on and so forth. So this terms has nothing to do with epsilon t, right? This terms has nothing to do with epsilon t. So they have their own epsilon t's, by epsilon t minus 1, epsilon t minus 2, epsilon t minus 3 and so on, right? So what happens is that yt has a correlation with epsilon t, but all these terms, all these yt's in the previous period. So I have written yt minus j with j greater than 0. So yt minus 1, yt minus 3, yt and so on and so forth. These terms have no correlation or no autocovariance with this term epsilon. This epsilon t and this lag values of yt are independent of each other, right? This thing you have to remember, that this epsilon t and the lag values of y does not have any autocorrelation, any covariance. So this term will be 0. So if you compare this, here you have covariance of epsilon t and yt minus 1, right? These two things are given here, so simply it will be 0. I hope this concept is clear to you. I will be coming to this concept time and again when we will be going into much complicated things. So fine, now variance of yt, simply this 1 minus phi square, when phi square is less than 1. Now this also comes from the property of stationarity, that when yt is stationary you can equate the variance of yt and yt minus 1. I have not talked about stationarity yet, but as of now just remember, when the process is stationary, it happens when this condition is satisfied. For an AR1 process, phi square mod of phi square is less than 1. So when this condition is satisfied, it means that the variance is the yt process is stationary, and hence the variance at t and t minus 1. So the time point doesn't matter. So variance will be the same, and that will give you this. Since I have not talked about this, I will not explain it further here. We'll see in some other cases, right? So this is for h equals to 1, right? H equals to 1, this will be the autocovariance. If you go on doing this, what you will see is that, okay, so it is basically phi into gamma naught. Phi into gamma naught. Now if you find out this for the second term, let me do it for up till second term. Covariance of yt minus 2. This is covariance of phi yt minus 1 plus epsilon t phi, okay, now right, yt minus 2 as it is, yt minus 2. So this will be phi covariance of yt minus 1, yt minus 2 plus covariance of epsilon t yt minus 2. Now this thing, as I have mentioned, this will be 0, and this term, if you simplify, will come out to be this phi square gamma 0. So you have to use the recurrence relation that is given to you in the question, and this will come out to be phi square. So here you got phi to the power 1 gamma naught. If you go on doing this using this lag value, so here lag value is 2, the phi power will also be 2. So you have to again replace yt minus 1 and then check. Let me do that. Yt minus 1. So this will simply be yt, okay, let me see the expression once. Phi yt minus 1, right? So yeah, plus epsilon t minus 1. Have I done this right? Yt is, yes, this yt minus 2, right? And this term is 0. So phi of, again, so here you have this term and this term and this term, right? So phi square covariance of yt minus 2 plus phi covariance of epsilon t minus 1 and yt minus 2. So this term is 0 and this term is phi square. Covariance of yt minus 2 is variance of yt minus 2. Since the process is stationary, the variance will be same, and this will be the expression when it is mandatory to write this, that phi square is less than 1. Only if this expression is satisfied we will have this expression, because again, coming from the property of stationarity we'll be talking about. So in general, In general, what happens when h equals to 0? The covariance is nothing but the variance, which is this, right? When h equals to 0, when h equals to 1 or h equals to minus 1, what will be gamma th? As we have found out, this is phi to the power 1, this is phi to the power 1 into gamma 0. Gamma 0 is variance, gamma 0. Variance, because we are using lag value of 0 for calculating variance. For h equals to 2 or minus 2, what will be autocovariance? This is simply phi square gamma naught. And using this in general, suppose h equals to k, so what will be gamma tk? It will be simply phi to the power k gamma naught, right? Gamma naught is this variance. I hope this is clear. Now if the value is given to you, okay, so here sigma square is given to you as 1, right? Normal 0, sigma square is 1, so you can replace sigma square everywhere. So here you will have sigma square is 1, so 1 upon 1 minus phi square, so it will be phi into 1 minus 1 upon phi square. It will be phi square into 1 minus 1 phi square, and it will be to the power k into 1 upon 1 minus phi square, right? I hope this thing is clear. So this will give you your autocorrelation function. So by this I have come to the end of this lecture. I know that this is a long lecture, but I wanted to make everything very clear to you so that you don't find anything difficult. If you have any questions from any part of this chapter, you can ask me, and I have given you multiple examples, multiple numerical questions, so that your concept gets very clear on this. And I have solved different types of questions depending on whatever can come in your exam. So if you like my content, then you can subscribe to this channel A in Economist and give me a thumbs up. I am making a lot of effort in I'm putting in a lot of effort in making this PPTs and then explaining things to you. So if you like my endeavor, then you can subscribe to this channel A in Economist for further content, and I'll be coming back with a video of stationarity in the next lecture, and I'll also solve some questions with that. So stay tuned for the next lecture, and I'll be coming back with the video of stationarity. Thank you for your time.